Hello, everyone, and welcome to the NESP Climate Systems Hub Understanding Marine Heat Waves webinar. For those of you I haven't met, my name is Helen Blaustein, and I'm the Victorian Knowledge Broker for the Climate Systems Hub, and I'm embedded within Victoria's Department of Energy, Environment and Climate Action. So today we're talking about marine heat waves. They've been in the news lately, so this webinar is very timely, and I've no doubt it will be a really interesting session and a chance for you to learn from our experts. I will introduce our first speaker in a moment. But firstly, I would like to acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional custodians of Melbourne, or Naarm, where I am joining you from today. We pay respects to their elders past, present and emerging, and would also like to extend respects to all Aboriginal and Torres Strait Islanders joining us today. We recognise the important role traditional knowledge plays in understanding Australia's climate. We know you're dialing in from across Australia, so please take a moment to think about the traditional owners and their contribution to the land from where you are joining from. A few housekeeping notes before we begin. Please ensure your microphones are muted. The webinar is being recorded and the link will be available from the Climate Systems Hub website after the webinar, and you'll also be sent a link to the recording. We encourage you to ask questions, and this can be done at any time by typing them into the Q&A function you can see on your screen. For me, it's down the bottom of my screen, but for others it might be on the side. We will address as many questions as possible later in the session, and I encourage you to get in early though with your questions, as we don't always have time to get to all of them. So first in, best dressed in terms of the questions. Now, I'd like to set the scene and provide some background about the Climate Systems Hub webinars. If this is your first one, welcome. The webinars are designed to provide an opportunity for learning and interaction with a broad range of topics and experts. We've had a great range of presentations over the last 12 months or so. You can find all the recordings on our website, and today's is going to be another one. So without any further delay, I'd like to warmly welcome our first speaker today. Professor Neil Holbrook is a Professor of Ocean and Climate Dynamics in the Institute for Marine and Antarctic Studies at the University of Tasmania. His interests and expertise are in the ocean's role in climate, ocean and climate variabilities, extremes and climate change. Over the past decade, Neil has contributed to advancing our understanding of marine heat waves. He is an elected fellow of the Australian Meteorological and Oceanographic Society. He is an investigator in the NESP Climate Systems Hub and ARC Centres of Excellence for Climate Extremes and 21st Century Weather. He is also recognised as a Clarivate highly cited researcher for the years 2021 to 2023. Welcome, and over to you, Neil.
Thanks very much, Helen. Thanks very much, Helen and Tani and all the NESP organisers for inviting us to give this webinar. I'm going to just give a little bit of a front-end overview of what marine heat waves are and give a little bit of background to what we're aiming to do and some of the impacts. And along the way, you'll see that there will be presentations followed up by John Reilly and Julio Salcedo-Castro as part of this team effort. So firstly, what are marine heat waves? What are they? So here's a qualitative definition for what they are. You could say that marine heat waves are discrete and prolonged warm ocean temperature extremes. So if we just take the ocean temperature extremes part first, that just tells you that, let's say for a particular location, that we're thinking about the warmest temperatures that people or species would experience at that particular place. They're discrete in the sense that they have a start and an end time, and you can think about them as having an onset and a decay. And the prolonged part is really capturing what a heat wave is, in a sense. So, you know, they have some duration, and that duration is effectively defined in a quantitative definition that I'll talk about later. So what do they do? Well, marine heat waves can cause substantial negative impacts, and amongst those are to key habitats or marine heat ecosystems. So, for example, tropical coral reefs. I guess their expression is largely through coral bleaching. Seagrass dieback. So seagrass can be pretty much anywhere around Australia, and kelp habitats, which occur around the southern part of Australia. And they're all important habitats for biodiversity, and basically, yeah, they're important habitats for marine species. And the other factor is around like fisheries, aquaculture, and tourism industries. And I'll talk a little bit about that as we go along. But as our oceans warm under climate change, marine heat waves are becoming even more problematic, and that's an ongoing pervasive fact. So this figure here is effectively, it's kind of a busy figure, but I just want you to focus largely on the left-hand side of this particular schematic. On the right-hand side, you can see there's some impacts, some of them of which I've already talked about, and that's in the water there on the bottom right. And then above there, you'll see a bunch of processes that John will talk about a bit later. These are these remote drivers of marine heat waves. But if we focus on the left-hand side of the schematic, firstly, in the top left quadrant, if you like, we've got the sun, and the sun is the ultimate heat source. So I'm really going to talk about two key processes, I guess, or two key drivers, local drivers that cause marine heat waves to happen. So we've got the sun as a source, and we're really talking about the upper ocean now in response. And you might get a high pressure cell, a blocking high, or a big high pressure cell. And when you get a big high pressure cell, you basically get suppressed winds. So the winds aren't normally caused, the winds would normally go across the surface of the ocean and might evaporate water. So the winds are suppressed, and the cloud covers tends to be reduced in those high pressure cells. And when you get these high pressure cells with suppressed winds and reduced cloud cover, you end up getting reduced heat loss from the ocean surface. And so the ocean is then able to heat up through to some depths. And usually they're quite shallow, maybe down to 20 or 30 meters or so. So that's the first one. And then the second kind of key type of marine heat wave comes from ocean currents. So then if you cast your eye down then into the bottom left quadrant, if you like, of the slide, you'll see this big red arrow that indicates ocean circulation, and particularly in boundary current regions, like let's say off Eastern Australia and off Western Australia, you've got strong ocean currents associated with, let's say, the East Australian current and the Huon current, bringing warm water from the tropics to higher latitudes. But sometimes those currents actually can intensify. And when you get an intensification or a movement off into a different location or some eddies associated with that, you can bring warm water into that region and cause a bit of an extreme. So they're probably the two key processes that really cause marine heat waves to happen. So how do we detect and analyze marine heat waves? Well, we've talked about the qualitative definition that marine heat waves are discrete and prolonged warm ocean temperature extremes. But back in 2016, Hobday and others got together and thought collectively about how we might actually try and detect them, and how we might therefore utilize, I guess, observational data sets to try and quantify how big they are and how long they last and all this type of thing. So satellite sea surface temperature measurements are key data sets that can be used to look at these. So here we've got an axis you can see with temperature on the vertical axis and time across the horizontal axis. And then on that axis, you can see that there's a jagged black line. Okay, so that's our, if you like, time history of temperature for a particular location. Okay, so we're giving a bit of a time series or a time history of how temperature might change over time. Then you'll see a blue line, a bold blue line. You can see it's like concave down. So you might imagine that that's reflective of how the seasons would change. So you might think that that's summertime, let's say, and then it would go down and then come up again through the winter. So this is the background seasonality. And so we express and try to understand marine heat waves in terms of also the background seasonal cycle. And that's our climatological average that's calculated based on some, let's say, 30 years of information. And it's quite smooth. And then in order to diagnose, if you like, or detect the marine heat wave, we need a threshold above which we consider it to be extreme. So in this Hobday definition, the 90th percentile has been chosen, and it was thought about for some time. And it's basically then gives us the top 10% of values that you might see at a particular location. And then there's a duration factor there, you can see. So that's the part that goes back to the qualitative definition of what is prolonged. And it was deemed at that particular time that 5 days was a good balance to consider not too much noisy data, but also that the persistence might be long enough to actually affect marine species. And then just a couple of years further down the track, a categorization scheme was developed. So now we've got this dashed line here indicating the time series. Our black bold line at the bottom there is our background climatology that in effect matches the blue line on the left. But then you can see when we get to the 90th percentile, we're starting at a category 1. And if you go 2 times that category, you get to category 2, category 3, and so on. And so we're really going from moderate through to extreme marine heat waves as categories that we might consider. So this next figure just then gives you a bit of a picture of marine heat waves around the world. Okay, so if we go back to the definition, we know actually at any particular point in space, according to that definition, we would expect to have marine heat waves about 10% of the time when we're up in the top 10 percentile. But you can see here there are some, you might call them iconic marine heat wave events that have happened across the globe. And you can see that there's coherence in the shapes of them in various locations. There's information there about the time when these actually peaked. And I think it's really important to note here that while you might get a marine heat wave 10% of the time at any particular location according to the definition, these shapes, these entities, if you like, are connected back to the kind of drivers that I talked about earlier, whether they be high pressure cells or whether they be associated with current systems. So I'm just going to really then now just outline a few that have occurred around Australia. And you can see there on the western side of Australia, there's one identified in 2011 called Ningaloo Nino. It's a marine heat wave, Western Australian marine heat wave, if you like, that occurred through the summer of that period. And it was particularly extreme and it had quite considerable impacts. And it really led to coining the phrase what a marine heat wave is. So the language around marine heat waves is only back since 2011. And then we've got 2 others you can see in 2016 in the Great Barrier Reef and in the Tasman Sea. Okay, so here I'm just going to click forward now. So here you can see back in 2016, there's evidence here for a coral bleaching event that occurred during that. It was a big El Nino Southern Oscillation event, big El Nino event during that time. And you can see that in the north part of Australia, there was coral cover loss of around 75 to 100% of coral cover, and it decreases as you go south. And you can see here in March 2024, there was a BBC briefing, if you like, announcing that the Great Barrier Reef was again bleaching. And so this is just a considerable concern, I guess, going forward, that the oceans continue to warm and these bleaching events appear to be having less intervals in time. And so the recovery time potentially for coral reefs is getting more difficult for them. But in the southern part of Australia, we also have what's been termed the Great Southern Reef, and this is more of a kelp habitat, and it also has incredible rich biodiversity and it supports many, many species. So if we go back to the 2011 Western Australian marine heat wave, there were devastating impacts associated with this in these almost like in kelp environments, but also there was coral along the coast that was bleached. There was seagrass dieback in Shark Bay, and there were commercial species loss. And if you look down in this figure here in the bottom left, this just shows from a paper by Wernberg and others, the percent canopy cover of kelp actually decreased right at the end from chugging along at around 80% canopy cover down to somewhere around 50% associated with that marine heatwave event. Then if we go over to the southeast now, we go to the Tasman Sea, you can see there's a marine heatwave there. And during that time, that was an unprecedented event also. And there were farmed oyster deaths associated with Pacific oyster mortality syndrome. There was problems with farmed salmon having poor performance. And there was evidence of abalone mortality in the blacklip abalone. And in December and January of this last year, 2023, 2024, there was very warm sea surface temperatures of the order of 2 to 3 degrees above average coming down the coast associated with these big anti-clockwise eddies, bringing warm water further south. And there was serious concerns about the marine heat wave impacting the southeast. And there were steps taken to do that. And I think some of those might actually be mentioned later on by Julio. So what are we doing as a team? So we're going to focus on the southeast. This is in the East Australian Current Extension region here. So if you look in that figure there up in the top left, we've got the East Australian Current bringing more warm water down the coast, the east coast of Australia. And this southeast region is a global warming hotspot. It's warming at 2 to 3 degrees fast, 2 to 3 degrees time, 2 to 3 times the global average rate, I should say. And it's a region that's particularly sensitive to all of these changes. John will talk next about regional ocean modelling. He will be talking about how he's trying to connect, I guess, the large-scale climate to the coast through this regional modelling effort, and looking at the offshore to onshore transports that bring that heat to the shore. And we're talking ultra high resolution here at the order of 3 kilometres grid. Julio will come in next and talk about his efforts to look at coastal and estuarine models and looking and doing some analysis on that at even finer scales, going from 2 kilometres down to hundreds of metres. And then we're really getting down to the scales that we believe are relevant to marine species and stakeholders and so on. And this is just a picture here of the types of things that go on, let's say, in the D'Entrecasteaux Channel that is really the, I guess, part of the studies that, that Julio will be looking at. And finally, here on the left, you can see what we've got is a classic figure here from, let's say, IPCC that shows how the connection is between the hazard, the vulnerability and exposure to create risk. What we're really trying to do in this particular project is characterize the hazard as best as we can. The vulnerability of species is really dependent on their sensitivity and also their adaptive capacity. And so ultimately then the risk to those species will be through the way that the species are exposed to the hazard and by how intrinsically vulnerable they are. So I'm at this point now, I'm just going to pass back to Helen and then we'll move forward hopefully and she'll introduce John.
Fantastic. Thanks so much for that excellent set of slides and background information, Neil. So just a reminder, please start your questions coming, put them in the Q&A function and we'll get to them later on. Next, I'd like to welcome John Reilly, who will give us an insight into that high resolution modelling that Neil referred to. So John is a PhD student at the Institute of Marine and Antarctic Studies within the University of Tasmania. His research is improving understanding of what drives nearshore marine heat waves, and these events, which can be economically and ecologically significant, are underrepresented in scientific literature. John's focused on developing this high resolution modelling capability to identify the physical processes that connect the nearshore environment to the offshore ocean dynamics. And having this information will help decision makers know more about past and future ocean states in relation to temperature extremes. Over to you, John.
Right, thanks, Helen. Yeah, so basically I'll give a run through of this exciting new modelling tool that we have, which can firstly look at how the processes that drive cross-shelf transport of heat onto the shelf, leading to marine heat waves inshore, and also look at how, with the changing climate, how that translates into the kind of coastal domain. So firstly, Neil's talked about these large scale events, and he's also shown that the greatest impact from these is when we look on the continental shelf in these shallow regions. So the continental shelf along Eastern Australia is shown in this figure by the orange band running down the coast. It's extremely narrow in points, which can make it pretty difficult to study and research, especially when we're looking at global models. But essentially, in these shallow ecosystems, marine heat waves can reach the full depth of the water column. And so in the north, that can lead to bleaching of the coral reefs. And in the south, again, as Neil mentioned, that can lead to kelp diebacks in these shallow regions. And this has cascading impacts on the economies through tourism and fisheries. So I'll also just mention that in this figure, we break up as a starting point in this kind of coastal investigation, we break up the shelf into these different bioregions. These are grouped by both the ecology and the oceanography along these points, and it just helps because when we start to look inshore, we need to consider kind of smaller spatial scales than we do when we look offshore. So it helps to identify distinct changes along the coast when we consider these different bioregions. Now, so the challenge. So global models are too coarse, as I've already mentioned. When we look at this figure on the right, we've got spatial scales on the x-axis, time scales on the y-axis. So global models fit somewhere in this blue box on the top right. So we have spatial scales above 100 kilometers and time scales from months. So anything below that, global models start to struggle to represent in their simulations. These are great for looking at climate change processes and climate variability like El Niño Southern Oscillation, but fall short of looking at the processes that connect the offshore to the coast. Then we have coastal models. These can represent scales anywhere from 10 meters to hundreds of kilometers, and look at the kind of really fast processes near the coast, such as river outflows and how they interact with the tides and the nearshore environment. And so these are great for looking at specific processes, but you can't really discern much about how the climate can change this nearshore region. Now we come in with these regional models, which are the connection between the global and the coast. So we're looking at scales anywhere from kilometre up to thousands of kilometres and from days to decades. And so the idea is that we can bring the climate information to the nearshore region, and we also can put these coastal extremes, like these coastal marine heat waves, in the context of our changing climate. So introducing our modelling tool that we are currently using and we set up, and the whole goal of this is connecting the climate scale to the event scale. So we're calling this a ultra high resolution regional modelling system. Basically, we start with a global ocean model, and when we say ocean models, we're talking about, say, a 3D space, so latitude, longitude, and depth, and then we step that forward in time. So a numerical ocean model. So we have this global model, then we draw this outer dashed line in the Southwest Pacific, and that's our large regional model. So that's at 10 kilometre resolution, the same resolution as the global model. And then inside that, we draw another dashed line, which is capturing all that interesting stuff that's happening in the East Australian current system. And then that's at a resolution of 3 kilometres, which is high enough for us to really get that cross shelf from the offshore to the coast interactions. So there is possibility also to, with the system we've developed, to move to even higher resolutions than that. And we have run a historical simulation from 1990 to 2018, but we also plan on doing some scenarios runs up to 5 to 30 years into the future. Yeah, so basically so temperatures and currents, they feed in from the boundaries from the global model. So you've got that climate information that feeds into the large regional model, then down into the small regional model. So you've got both the climate variability and the local processes. Right, so now a demonstration of the difference between an observational product that we use to validate the models, our global model, which is in the middle, and then our regional model, which is in the right-hand side. Basically, the key point of these is to show that near the coast, which is represented by the solid black lines in these three figures, this is showing sea surface temperature. We have much finer detail in the high resolution model on the right than we do in the global model and the observational product. And with high resolution comes a better representation of the dynamics and just the processes that lead to climate extremes or ocean extremes. Now, I'll just run this model forward a bit and we can see how these warm temperatures
You muted.
Sorry. Yeah, I'm good now.
Yeah, good now.
Yeah, it should be fine now. So yeah, this is a perfect point to pause it. So we can see the EAC jet in all three models, but obviously the highest resolution model shows the most detail. And this is a key point where the EAC separates from the coast. In the observational product, it's just so happened to separate further south in this particular time series. But yeah, so where it separates from the coast, you have this strong gradient in temperature, which leads to a lot of upwelling and interesting stuff happening. Yeah, that interacts between the offshore into the coast in this specific region. Now, if we move forward a bit further, we start to move into the eddy-rich EAC extension region. And here's where you have a lot more chaotic interactions between offshore and the coast. Yeah, so we see that heat come down, and if we pause it now, yeah, so essentially what we should be able to see is that the high resolution model has a lot more detail and yeah, is going to be much better at looking at nearshore, yeah, kind of those processes, but also in capturing that climate influence in the coastal region. Right, so forward, sorry. Can I move to the next slide? Yeah, so basically what we're looking for in terms of the processes that lead to this offshore to onshore connectivity. Here's a simple example of, yeah, so how the EAC current influences the temperatures. There's these eddy configurations. So eddies are these circular kind of rotating currents that happen especially in the EAC extension region. And what you see between, say, 35 to 37 degrees south in the left-hand figure, you see the blue clockwise rotation to the north and the red anti-clockwise rotation to the south. And this is something we call an eddy dipole that can lead to these really strong onshore jets. And in this particular scenario, there just happened to be an offshore marine heat wave that got caught up in this eddy dipole. And so that heat becomes injected into that coastal domain. It's a really localized marine heat wave, but it can have a severe impact in that kind of specific coastline. So that's the kind of processes we're looking to further characterize in this high resolution model. Now for more of a climate look at the near shore. So long-term temperature changes in the shelf are non-uniform. So if we look at this figure on the right, this shows the sea surface temperature trends within those different bioregions near the coast. And basically it's non-uniform. So to the north of about 35 degrees south, we have pretty slow warming trend. There's not too much change happening, but then as we go south of about 35 degrees south, which is about the Bateman's Bay region, we start to see a lot faster warming over the last few decades. And the really interesting thing is that this bioregion, the Freycinet bioregion, number 48 off Tasmania, has about 3 times the warming of any other, 3.3. Yeah, I think over 30 years, I think it's, yeah, I haven't quantified it, but you can clearly see that it's a lot faster warming than anywhere else. So that's due to the EAC extension becoming more intensified in terms of the eddies, bringing more heat down, and that's this particular coastal region, yeah, appears to be most exposed to that heat. And just a quick question for the chat. So looking at these trends, does this sound familiar to maybe what you've observed or your understanding of the coastal the changes in the coastal temperatures that we've seen, maybe from an ecological or a fisheries point of view. And finally, looking ahead. So firstly, I want to look at what's driving these coastal trends, what's driving that difference between the kind of north of the this 35 degrees south and to the south. And I also want to look at, these future climate simulations to understand how much the temperatures will change into the future. Finally, we're working with marine ecologists to link these temperature changes to the species changes. And just a final question for the chat. So are there any locations that you would like more greater focus, such as sensitive marine areas, that we can set up even higher resolution models to understand what processes are driving those temperature changes? I'll now pass over to Helen to introduce Julio. Thank you.
Excellent. Thank you very much, John. And just to those online, so John issued 2 challenges there, I think, to everyone to please add into the Q&A any examples that you might have from your own experience of where marine heat waves, or what you think might have been marine heat waves, might have occurred. And secondly, if there's any particular regions of interest that you think the team might wish to explore a little bit further, please add that in as well. So next, I'd like to welcome Julio Salcedo-Castro. And Julio is a lecturer of physical oceanography in the Institute of Marine and Antarctic Studies at the University of Tasmania. His research specialty is coastal oceanography and estuaries, especially the response to atmospheric forcing and the impact of extreme events in these locations. He uses modelling, remote sensing, and observations to describe coastal oceanographic processes. Julio has studied coastal environments in Canada, Chile, and Brazil. And in Australia, he's worked on mapping stresses on the Great Barrier Reef. He's now studying the impact of marine heat waves on the Huon estuary and D'Entrecasteaux Channel in Tasmania. So welcome to you, Julio.
Thanks for the nice introduction, Helen. Hello, everyone. And well, you have seen, we started with a very regional and historical overview by Neil, and then we moved to a kind of a regional high-resolution approach to study marine heat waves. But now it's my turn to describe the impact of this episode on a very, very local scale. And to do that, I'm using the Huon estuary D'Entrecasteaux Channel as a case study. And you might ask why? Well, estuaries are very interesting systems, relatively complex. We have many here in Australia, so that's one of the reasons. So I'm using this as a study case, I just said. As you can see, Neil also mentioned that normally estuaries concentrate the high biodiversity. So there are many activities, fisheries, aquaculture, recreation activities, cultural activities. So they are very interesting and relevant areas. So that's why the reason of choosing this as a study case, and this one in particular here in Tasmania. And one particular aspect of estuaries, some of you might know, is that they are very stratified systems. So if you look at this picture, you can see that those arrows, white arrows, the continuous one represent the top layer. It's kind of brackish water coming from the river and going to the ocean. And then you have a second layer, a bottom layer, which is a thicker one, which is composed of seawater coming from the ocean. So that's a sort of a tricky part of this system. Well, let's take a look at this particular vertical distribution of temperature. So if you look at these schematics on your left, I guess, you can see kind of normal vertical distribution of temperature. So it's essentially higher on average on the surface, and then it's a very stratified, and then it's a lower temperature as you go deeper. But when we have a marine heat wave, what happens in some cases is that you have higher temperature at the surface, but also throughout the whole water column. what are the consequences of this type of phenomenon in this coastal system according to the recent literature? So there's not much research about this particular type of system. So potentially we can have a less vertical mixing because it's a more stable system. It's more stratified depending on the type of marine heat wave we have. So that implies a longer residence time, which is not good in terms of nutrients, biochemistry, or some potential contamination events. So, but more importantly, this could affect the system having lower dissolved oxygen solubility. So this one has been already observed in other parts of the world, but also higher acidity. And in some areas, some co-occurrence has been described. So when you have higher temperature, obviously you have lower oxygen and higher acidity affecting the organism. So consider that as for a single organism or for some specific type of communities. And at the same time, there could be a sort of a synergy of these variables, of these processes, along with some other variables that we should consider. So the impact on organisms, and Neil already described some of them, it's like obviously there's some metabolic stress. Diseases obviously lower growth rate. Some species are very happy with this marine heat wave. Some of them are not really. We have the typical example of the sea urchin, the occurrence of harmful algal blooms, like the one that was described in southern Chile. And like I said, this can affect the whole community, benthic community, and some foundation species like kelp, and some vulnerable species, as the typical example is the red handfish. As a consequence, this could have a negative impact on salmon farming and oyster farming, as you can see on this recent news. So what am I doing? I'm using different data sets, so higher resolution models to better describe the circulation in this complex area. So the first one is the ETAS, which provides a sort of climatology. So how can I say? It's kind of average condition, the traditional or normal condition for this system. And then I'm using a TASE model output, which is a model that was recently developed by CSIRO. And this model has been validated. As you can see, it has about 200, 100 meters resolution, horizontal resolution, which is really good if you really want to describe the spatial patterns in terms of circulation, recirculation areas, etc. And I'm very lucky because I'm also using some observations from this broad-scale environmental monitoring program, and so that I can compare and verify the result from this model output. And the idea is to study the two more important marine heat wave events. So the strongest one was in 2016, 15-16, which was mostly ocean driven. And then there was another one in 2017-18, which was mostly surface atmosphere driven. So you can see this timeline on the bottom representing the database I'm working with. So let's talk about some of these. For instance, okay, let's talk about one profile. If you remember the vertical profile I showed you, let's assume that you put all those profiles one after another to construct this timeline. And this represents the vertical distribution of temperature. And here you can clearly see these two events with a higher temperature, higher than 18 degrees, which was observed up to depths of 25 meters, which is quite strong if you consider that this could affect the bottom communities, benthic communities, kelp, etc., abalone. And then the other one was mostly affecting the surface, but it was a very strong event anyway. So when I use the model for the same station, same idea, putting all this it's a sequence of profiles together for that period, the top panel shows you the climatology, the kind of average condition for that area from September to May. And the panel in the middle shows you the marine heat wave. And you can see the difference in terms of temperature. It was above 20 degrees. So if you want to estimate the intensity, which is the difference between the average condition and the marine heat wave episode, you can see the difference was higher than 4 degrees. So it was a very intense thing, and you can see the difference affected up to depth of 15, almost 20 meters. If you want to compare, if you remember the schematic at the beginning, I showed you the profile, the temperature profile. So that's what happened during this marine heat wave. Just to give you an idea in terms of oxygen solubility, on the bottom, this table shows you the difference in terms of dissolved oxygen solubility. So when you move from 15 degrees, you have a solubility of 8 milligrams per liter, but when you have 20 degrees or higher, the solubility decreased by about 10%. So that you just need to consider that for a long time, for many days or even some weeks, and that will cause a lot of stress to some type of organism. Okay, so this animation is just to emphasize again the idea of that the marine heat waves are not just affecting the surface. The panel on your left shows you the vertical distribution of temperature along this estuary, along the section represented there. And then you can see that these events can affect from the surface to the bottom in some cases. So next, or what I'm working on right now, it's obviously we need to get a kind of whole vision of this system. So that's why we need to analyze some current data, wind data, the river discharge, because not just in terms of river discharge, also in terms of river water temperature. It has been observing some other systems. Local data, so radiation, local radiation, and local wind stress. As Neil said, normally wind is weaker during the marine heat wave, so that means there's less opportunity for mixing to occur. So yes, that's the idea of my study. I'm working on that, so I hope to have some very interesting results about these variables for the next month, hopefully. So now I'm going to pass over to Helen, probably, or Neil.
Yeah, thanks, Julio. Yeah, I'll just finish off with this summary slide, and they're pretty high level. It's a pretty high level summary, but it also has a goal of, and just reiterating what we're really doing, and it might actually somewhat answer some of the questions that are coming through in the Q&A. Firstly, I guess, marine heat waves, as I've said, can cause substantial negative impacts to marine ecosystems, fisheries, aquaculture, and tourism, biodiversity as well. John has already talked about his work that he's looking at regional ocean modelling to investigate offshore to onshore processes and heat transfers at ultra high resolution, so of the order of 3 kilometres to the southeast Australian coast. And really, we're going to be basically looking at historical climates and future climates, and we'd really like to look at, sort of the 5 to 30 plus year time frame going forward. Julio's talked about coastal and estuary model simulations at sub 3 kilometre scales, so 2 kilometres down to hundreds of metres, to provide information at scales relevant to species, habitats and stakeholders. And all of this work at the moment is focused on this southeast region and into the D'Entrecasteaux Channel and so on. So overall, I just want to reiterate that our goal really is to generate the best and robust estimates of marine heatwave metrics. So it's essentially things like intensity, spatial extent, and timing to inform studies. And primarily, these studies will be external to this project. We're not really ourselves, working on risk per se, but part of that whole risk analysis is just trying to understand the hazard as best as we can. So that's where our effort is really trying to characterize those marine heat waves as best as we can, so that those studies can actually focus on understanding that risk. in terms of species, marine ecosystems and industries. I'll pass back to Helen.
Excellent. Thank you all for those that really fantastic summary of marine heat waves. So it's Q&A time for the next, I've got quite a few minutes, probably, almost 10 minutes of questions possible. There's a number in the chat, so probably just work through them as I come to them. And the first one is potentially to Neil and also John. Can your model be used in other parts of Australia?
I'll pass that one to John. I think he has the answer.
Yeah. So a really cool thing about the kind of what we've set up is this whole relocatable modeling tool. So basically, me and some colleagues at ANU have set up this Python package where you can just draw a box essentially and over anywhere all over the globe. And if you have the kind of global parent model to force that regional model, you can set it up anywhere, which is, one of the key things we've been working on this past year. So, we were looking at a model in Western Australia for a while. It turned out that the area we were looking at was a bit too shallow for this sort of model, and it probably would have been more suited to one of Julio's kind of coastal estuarine models. But you can basically set one up anywhere.
Thanks, John. And just to follow up, so will the model, once your research phase is completed, will that be available more broadly for anyone to use? You've kind of hinted at it, but I'm not sure if, you have the answer as to how that would physically happen.
Yeah. I'm not too sure about the specific model output from these simulations. Neil might have some idea about how accessible that is to the public, or?
Look, I think we can make them available to the public. I think that would be a great resource.
Yeah.
Thanks so much. So I think the clue there is to stay in touch with the Hub via our website and other material that's published. And once, John's project comes to an end and other research evolves, we'll let you know how to access the information. Thanks for that. So the next question is from Pethy. Is there a link between these long-term marine temperature changes and future opportunities for the blue carbon economy? So another way she's phrased it is marine heatwave science being considered in the blue carbon economy, and how? Who would like to take that? Maybe Neil?
Yeah, thanks, Peppy. I don't personally have the answer to that. CSIRO may be working on this through their carbon group, but I guess as I guess I wrapped up, what we're really focusing on here is just trying to better understand the hazard itself, and the blue carbon part isn't really part of this project. But I think it's I think there are people potentially at CSIRO who are working on this.
Thanks, Neil, and thanks, Pethy, for the question. And I think, from what we've learned today, it's a particularly evolving and emerging area of science. So I guess we do expect there'll be many applications of this research and other research in the future to help inform decisions. Okay, just another question from the Q&A, and please keep them coming. We've got time for a few more. So a question from Arani: how can we better fund and operationalise regional models around Australia to better serve end users and industry to understand these real-time coastal ocean conditions and marine heatwave events? That's a big question. I'm not sure who would like to take that. Maybe Neil again, if that's okay.
Yeah, these are really big questions. I mean, there were discussions with IMOS, let's say, in the Integrated Marine Observing System, to try and vitalize, I guess, thoughts around having a sort of a high resolution coastal modelling around Australia. But I'm not sure where that's at. I'm not actually personally part of IMOS, but that would be one mechanism. I know it's primarily about observing, but this has been a long-standing thing that, you know, individuals have their regional models at different places around Australia, but having something much more integrated has always been something that we've been striving to try and push for, but it all comes down, I guess, to funding and support for that. And so at the moment, coastal models go on as sort of individual patches, let's say, as far as I can see.
I might just add to that. Yeah, so I'm a part of the group that it's called the Australian National Coastal Ocean Modelling System Group, and that is basically the goal of that group is to integrate all of the different models that are used all around Australia. Yeah, so because there's some used further up. So e-reefs for the Great Barrier Reef, and trying to integrate how they feed into yeah, the models further south and things like that. So the acronym is ANCOMS for that. Yeah.
We might actually be able to put that acronym in the chat, or if you can, John, that'll be really good if you can do that. Okay, next question is one for Julio. What about the impact? So you talked about the impacts in Tasmanian estuaries. Do you have any insight into what this could look like in other estuaries around Australia?
Well, that's an interesting question. Actually, that's the idea is to extend this study to some other regions, bigger systems. It really depends on the system, because it's if you compare this with Burdekin River or Fitzroy River on Queensland, it's absolutely different in terms of the influence of the river plume in that area. Yeah, but we can start at, this is a kind of starting point. So the idea is to compare this and take some other cases, probably from Western Australia, probably from New South Wales. I think Sydney Harbour would be a very interesting system to study next.
Excellent, thanks, Julio. And does it matter, sorry, question for me, does it matter how far inland the estuaries go, or does that, to what extent does that have an impact with the river waters or other waters that are coming in to the estuary?
Well, that's a good question. It's also connected to a question I just I responded, because in some cases, when you have a very, very strong heat wave, not just marine heat wave or heat wave episode on land, obviously the river water temperature is higher too. So we necessarily have to consider the river water temperature, which is complicated sometimes because we don't have that information. So we really need to estimate that from air temperature. But yes, when it's about estuaries, we really need to consider that variable. River water temperature is important.
Thanks, Julio. So a question, again, I think this might be for Neil. So under the definition of marine heat waves, is there a lower limit in terms of spatial scale to be defined as a heat wave?
Oh, okay. So spatial scale was actually discussed, I think, in that Hobday paper originally, but and there are moves afoot and efforts now to try and characterize marine heat waves in terms of their spatial shape and everything like that. But there's no formal exclusion or decision making around what's big enough to be a marine heat wave. It's more of a detection in terms of at a particular location, let's say currently, as to, you know, the length of time that it must exist for and the threshold above what it must be. Because if you think about species, they feel a heat wave locally. They don't really care necessarily how big it is, but dynamically, I think that really does better connect if you want to try and think about predictability to the type of processes that are causing it. But in terms of straight out, you know, detection definitions, the spatial scale currently isn't really, doesn't have a minimum threshold.
Excellent, thank you. And just one final question from Greta, who was probably a nice way to wrap up these questions. She just wanted to check the definition of marine heat waves. Are heat spikes counted as part of an onset or decaying period of heat?
Yeah. So
Thank you.
it's a good question, and she's picked up very well from the figure that there's heat spikes on the figure, but I didn't actually say that they're not considered as a heat wave themselves. They're considered separately. There is this kind of little bit of a nuanced point in the definition that says if you have a break between two successive marine heat waves of sort of 2 days or less, it's considered to be the same marine heat wave. But spikes per se, no, they're considered as just extremes.
Fabulous. Thank you so much, Neil. So we're about done for time here, so that and also no more questions that I can see. So thank you so much for such excellent presentations, Neil, John, and Julio, and to all of you for your active participation and engagement in the session. And I'd like to take the opportunity to thank you all for supporting the Climate Systems Hub. And we really hope you have taken something from today, be that learnings, connections with others, or a wish to stay involved in marine heatwave discussions going forward. We've got some other great webinars lined up for the rest of the year, so please subscribe to our newsletter, and you can do that via the QR code there or via our website or that email address, which is on your screen, and keep an eye out on your inbox for more information about what's coming up. Please also spread the word to anyone else you think may be interested. We're planning more webinars, as I mentioned, throughout the year. If you have suggestions for future topics, please also email those into us at info@nesp2climate.com.au. And on the website, you can scroll for regular news and science updates, and the address is just there on the screen. And before we finish, we'd really value your feedback. So please provide this via the email you'll get when you get the recording link, hopefully later this week. And just a thanks again to our presenters and for all the others who have been really active behind the scenes to make today happen. And we'll see you next time. Thank you very much.